Let's try to understand the concept of conductors, insulators, and semiconductors. Most of the solids are usually conductors and insulators. What is a conductor? Conductor is a substance which has good number of free electrons. You know the concept of free electrons? That electrons which are on the outermost shell are usually free. So if the solid has more number of free electrons, it is called as conductors. As the number of electrons are more, it can allow easy flow of current, therefore it's a good conductor. And insulators are those substances which do not have free electrons. They have bound electrons which do not contribute for conductivity. So insulators do not contribute for conduction, and insulators have practically no free electrons. And there is one more substance which has conductivity intermediate between the conductors and insulators. Okay, so they are not as good conductor, they don't have as good conduction as conductors, but not that bad as insulators too. They have conductivity under certain circumstances. So those substances which have conductivity lying between conductors and insulators, we call it semiconductors. Examples: carbon, silicon, germanium. These are the examples of semiconductors. Because these semiconductors, outermost electrons are not that rigidly bound, okay, and not that rigidly bound as insulators. In case of insulators, the outermost electrons are rigidly bound, so they do not become free, but not as free as conductors also. In conductors, the electrons in the outermost shell are very loosely bound, so they become free and they can easily contribute for conduction. But semiconductors, they are not that loosely bound as well as not that rigidly bound. Okay, under certain circumstances, electron can be free and they can contribute for conduction. So we'll talk about semiconductor now in much details. But at absolute zero temperature, that is at 0 Kelvin, semiconductor will also behave as an ideal insulator. That means in that situation, semiconductor also will not contribute for conduction. Let's try to understand energy bands in solids. We have already understood the concept that electrons in solid or any substance lies in the particular orbits. We have a name for orbit like S, P, 1s, 2s, 2p, 3s, 3p. So these are the orbits name in which the electron can lie. Okay, so let's here we have on diagram. You can see in the figure 2p, 3s, 3p. Okay, these are the energy levels. These are the orbits in which the electron can lie. Okay, in the figure you can see the energy level 2s, 3s, 3p. These are the energy levels for one atom. So a solid may be consist of n number of atoms. Okay, so if you have n number of atoms, then we can have n number of 2s, 3s, 3p levels, and in that of n number of 2s, 2p, 3s, 3p levels, the electrons will be there. Okay, they will be filled up in each atom independently. For one atom we have 2s, 3s, 3p and its levels, so the electrons may be filled up. And under the atom again we have 2s, 3s, 3p and its levels. In that atom also the electrons are filled up, and in each atom the electrons are filled up independently of the other atom. Okay, so if there are n number of atoms, then we have n number of energy levels here, and in that number of energy levels we have electrons filling up in that each atom. So what happens is that usually what happens when n number of atoms are brought together, so the higher energy levels like here 3s and 3p energy levels interact with the other atom energy levels. Okay, so when 3s, 3p energy levels of one atom interact with the 3s, 3p energy levels of the other atom, they further split into n times. Okay, they further splitting into n times, and this splitting of these energy levels finally form the energy band. Okay, because this splitting will happen so many times, n times, that it almost becomes continuous. Okay, they are no longer discrete. This 1s, 2s, 3s, 3p energy levels are discrete, but once they are split into n number of lines, okay, because of the interaction of the other atoms, then this almost becomes continuous, and this continuous energy levels, we call it energy bands. Usually the splitting will take place for higher energy levels, not for the lower energy levels. Lower energy levels highly split because uh, these lower energy levels are the levels in which the bound electrons are there. So bound electrons are not that much affected by the presence of the other atom. Okay, but only the valence electrons are usually affected by the presence of the other atoms, and therefore the valence energy levels or higher energy levels usually split because of the interaction of the other atoms. Okay, and because of the splitting of the higher energy level, they form the continuous energy levels that we call it energy band. Okay, therefore we can say the energy bands in a solid corresponds to energy levels in an atom. Now these energy levels, there are various energy levels. Okay, these energy levels may overlap or may not overlap also, depending upon the solid. If they overlap here, you can see the energy levels are overlapping. Okay, energy levels are overlapping here, but sometimes they do not overlap also. If the energy levels are not overlapping, see, this is one energy level, this is another energy level. Okay, this is another energy level. So in between you can see some gap is there. This is the gap, we call it forbidden bands. What do you call it? Forbidden bands. There are 3 energy bands. Okay, and in between you can see some gaps. Why do you call it forbidden bands? In this region, no electron can lie. Electron can lie only within these energy bands. Okay, because electron cannot have any value of energy. Electron will have energy of these energy bands only. Okay, so in between, if there is a gap, that means the electron will not lie there. So that is called forbidden bands. Okay, so sometimes you can see here overlapping energy bands are there, so electron can slide in between. Here also there is no forbidden band. So it is also possible that electrons can have forbidden band or overlapping energy bands also. Now we'll talk about this in much detail. Now what is more important here? The important thing is, now we'll try to find out these energy bands. What are the energy bands for insulators, conductors and semiconductors? How are they different? Okay, how do they look like for conductors? Let's try to understand for conductors. So here we have taken the example of sodium. Sodium is one of the conductor. Okay, it has 1 electron on the outermost shell. So you can see 1s, 2s, 2p. There are different energy levels are there. Okay, and out of this, 3s, which is the highest energy levels, are split because of the interaction with the other atom. Okay, so this 3s energy level is split into energy bands. Here you can see. So here 2 bands are there. Okay, one is outermost. This is your valence band in which for sodium atom it has 1 electron, and there is one empty band above the valence band. That empty band we call it conduction band. Okay, so these are energy bands. We have valence band and conduction band. Both of them are overlapping each other. There is no gap in between them. Okay, so this is your valence band and this empty region is your conduction band. Okay, and it has 1 electron on the outermost shell. So splitting is there only in the 3s energy level, not in 2p, 2s and 1s level. So let's try to understand the concept of energy bands in conductor, because this is an example of conductor. So what happens here? For conductors, these 2 energy bands, that is valence band in which the 1 electron is there and conduction band which is empty, both of them are overlapping here, and the valence band is partially filled band. Okay, both of them are overlapped. There's no gap in between. So that means what happens, by any reason, so this electron which is there in the valence band, if they acquire some additional energy, if I apply the electric field in the sodium atom, then this electron can acquire the energy and can go to the conduction band. Once it goes to the conduction band, then it can move freely in the conduction band, and that this is how the current flows. Okay, current will only flow if the electron from the valence band goes to the conduction band. So in case of conductor, it is very easy because both of them are overlapping. So if it gets some additional amount of energy due to the electric field, then it can easily go to the valence conduction band and it can conduct, okay, electricity. This is example of sodium. So here the valence band is partially filled and conduction band is just above the valence band, overlapping each other. Again you can see beryllium is also one of the good conductor. Here we have 2s2. You can see 2s2 is the valence band, and just above this we have a conduction band. Okay, so if by some additional amount of energy is given to this 2s electron which is there in the 2s orbit, because there are 2 electrons in the 2s energy level, then one of the electron will go to the p, lowest level of the p. Okay, and further if you give some amount of additional energy to that partially filled 2p energy levels, then that electron will go to the conduction band, and the conduction band, once it goes to the conduction band, again if you apply the electric field, then the current will start flowing through this beryllium. So what is the main feature of this conductor? A partially filled valence energy band is a feature of conductors. A partially filled valence energy band is a feature of the conductor. So here in case of sodium, there is already one electron on the outermost shell that is partially filled. Okay, but in case of beryllium, because of some additional energy, one of the electron from the 2s will go to the 2p. Okay, and if you give more energy, then it will go to the conduction band, and that will contribute for conduction. So there is no energy gap. So both conduction band and valence band are actually in the overlapping each other. Now let's talk about insulators. In case of insulators also we have both valence band and conduction band, but there is a gap in between. They are not overlapping. So in case of conductors, the valence band and conduction band was overlapping, they were same. But here there is a gap, and the energy gap between them is 7 electron volt. 7 electron volt is very high energy. So here the valence band in case of insulator is completely filled. Okay, it's completely filled, and conduction band is completely empty. So if you give energy to this electron will not have that much of energy to go to the conduction band. As a result, they will never contribute for conduction, because no electron will go to the conduction band. Okay, so it's very difficult for insulators to conduct, because usually the valence electrons, they at least need 7 electron volt to cross the gap, but usually they are at room temperature, they have only energy up to 0.025 electron volt. Okay, so 0.025 to 7 electron volt is very high energy. So if an electric field is applied in the valence band, then the electron will not move in the valence band, because valence band is not free. Okay, there's no place for the electron to move. Valence band is completely filled up, but that electric field cannot provide 7 electron volt amount of energy for the electron to cross the gap. Okay, because it is very high amount of energy. If it could provide 7 electron volt to cross the gap, then the electron, if it reaches to the conduction band, they may also contribute for conduction. But electric field alone cannot provide that high amount of energy for the electron to cross the gap. Because of that, insulators will never conduct. Semiconductors. Here also we have a valence band and we have a conduction band. Okay, and the example of semiconductors, silicon, germanium, and there's an energy gap between them, but the energy gap is almost very small, 1.1 electron volt for silicon, and for germanium it is 0.7 electron volt. Okay, we have to remember this energy gap value. So if the electron in the valence band can cross this gap, if it acquires 1.1 electron volt energy, then it can cross the gap and reach to the conduction band. Once it reaches the conduction band, then it can freely move in this empty conduction band and contribute for the current. Okay, so at room temperature, what happens? Some of the electrons, not all the electrons, can get some thermal energy sufficient enough to cross this energy gap 1.1 electron volt and can go to the conduction band. Once it can go to the conduction band, if the electric field is applied, then they can get some additional energy to move in this conduction band. Okay, because of this movement of the electron in the conduction band, due to electric field, there is a current. So there is a limited flow of current because not all the electrons can move to the conduction band. Therefore, in case of semiconductor, the conductivity lies in intermediate between the conductors and insulators. Let's try to understand the concept of electrons and holes in semiconductors. So as I told you, in case of semiconductors, because of the thermal energy, some of the electrons can cross the energy gap of 1 electron volt in case of silicon and go to the conduction band. But once the electron from the valence band goes to the conduction band, they leave behind an empty space that we call it hole. So hole is nothing but absence of negative charge electron. So we can say hole as a vacancy created in the valence band, okay, which is nothing but equal to the presence of equal positive charge. Okay, absence of a negative charge is equivalent to the presence of equal positive charge. So if electron is not there, negative charge electron is not there, it means there is a positive charge, hole is there. Okay, so hole is a sheet of positive charge of magnitude equal to the charge of electron. So that's the concept of hole. It's just the absence of electron which has the same magnitude of charge as electron, but only thing is that it is positive. Okay, so this electron which goes to the conduction band, if electric field is applied, they move in the conduction band, and the hole which is there in the valence band, because of the electric field, they move in the valence band, and because of the movement of these electrons as well as holes, we get the current in the semiconductor. Okay, and in case of semiconductor, the temperature increases, the conductivity will also increase. Why? Because more of the electrons will from the valence band go to the conduction band. If more of the electrons will go to the conduction band, the conductivity will also increase. So temperature increases the conductivity in case of semiconductor. Now there are different kinds of semiconductors. There are two actually: intrinsic semiconductor and extrinsic semiconductor. What is intrinsic semiconductor? Intrinsic semiconductor is a pure semiconductor. Pure means free from impurity. Okay, and this electrical conductivity of this pure semiconductor is not that good. Okay, it's very less. Okay, so pure germanium and pure silicon are the examples of intrinsic semiconductor. Let's try to understand this one. Germanium electronic configuration is this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p2. So in the outermost shell there are 4 electrons, 2 and 2. In case of silicon also, in the outermost shell there are 4 electrons. So both germanium and silicons have 4 valence electrons on the outermost shell. Okay, so here we can see it in the picture. Plus 4 for the 4 valence electrons. This is one of the germanium atom. Plus 4 is the charge of the nucleus, and you can see electrons over here. Valence electrons, 4 valence electrons. Similarly for this atom we have 4 valence electrons. Similarly for this atom we have 4 valence electrons. In the picture we can see the 4 valence electron of each atom. Here you can see the 4 valence electrons, and these 2 electrons of each atom is bonded together by the covalent bond. You can see there are 4 covalent bonds. Here you can see nicely this electron and this electron shared together, this electron and this electron shared together, this electron and this electron shared together, this electron and this electron shared together. Since there are 4 valence electrons on the outermost shell, so in case of silicon or germanium, you can see the 4 covalent bonds of each atom. Okay, so this is a pure germanium and pure silicon atom. Now let's try to understand what happens here. At absolute 0 temperature, okay, that is 0 Kelvin, what happens? These electrons are very tightly bound. These electrons are very tightly bound. Because of that, no electrons from here will leave this space. Okay, no electrons from here. It's just like this picture. No? These electrons which you can see over here, they are valence electrons. So they will be lying on the valence band here. They will be lying here, valence band. Only if the electron from the valence band go to the conduction band, then only they will contribute for the current. So in the room temperature, all the valence electrons will be over here
they don't get enough energy to go to the conduction band, so they will not contribute for current in case of absolute zero temperature. But as we go to the room temperature, then some of the electrons will get sufficient energy. You can see over here, suppose this electron gets sufficient energy, then this electron will come out from this valence band. It will come out and go over here. You can see the bond is broken, so it come out and moved over here. That means it become free now. That means this is happening. Some of the electrons from the valence band is going to the conduction band. Okay, once it goes to the conduction band, it becomes free because this place is empty. Okay, and once it becomes free, if I apply the electric field, then electron will move towards the positive terminal of the battery, opposite direction of the electric field, because electron is a negative charge, so obviously electron will move in the opposite direction of the electric field, F equals to minus QE, and holes will move in the valence band. Actually, holes do not move. What actually happens is that this, let me show it over here. Suppose you can see over here, this electron from here, move to this place. Therefore, there is a hole over here because electron is moved to this place. Now what happened? This electron will again move to this hole. If this electron will move to this hole, then hole will be created over here. Again, this electron will move to this hole. Okay, and this hole will be filled up. Again, there will be hole over here. Again, this electron will move to this hole. So what is actually happening? There is no actual movement of hole. Actually, the electrons in the bound orbit here, you can see here. Suppose this electron, there was the one electron over here, and this electron moved to this conduction band. So there is a empty space here. So there is electron over here. This electron will move to this region. Okay, there is an empty space, and this electron will move to this region. Okay, and there is an empty space. So it looks like that hole is moving towards right, but electron is moving towards left. Hole doesn't move, the electron is moving, and this electron will, there is a hole over here, so electrons will move to this side, and there is a hole over here, like this. Okay, so what happens? The free electrons will move in the conduction band in the opposite direction of the electric field, and the holes will move in the valence band in the same direction of the electric field, because hole is the positive charge, so F equals to plus QE, same direction of the electric field. Electron is the negative charge, so F equals to minus QE in the opposite direction of electric field. So both electrons in the conduction band is moving, holes in the valence bands are moving, and because of the movement of the electrons and holes, we are getting current in the semiconductor. So we say in semiconductors, both electrons and holes constitute the current, and total current is the sum of the two current. You can see as we increase the temperature, more number of electron and holes are generated. If the electron is generated, then holes will be also generated. Okay, so number of the electrons over here, number of electrons in the conduction band will be same as the number of holes in the valence band, because absence of the electrons is only the holes. So if the 10 electrons went there, then 10 holes will be created in the valence band, right? So that way the number of electrons and number of holes are same, but it doesn't mean that the contribution to the current by electron is same as the contribution to the current by the holes. There is a little trick there you have to understand. Suppose even though 10 electrons in the conduction band are moving, and they will give you some current, and 10 electrons in the valence band are moving, they will also give you some current, but the whole current is not same as the electron current. Why? Because these electrons are moving in the empty space, therefore there is less resistance, but the holes are moving in the filled space, because this is a valence band, the electrons are there, therefore they will feel more resistance. Because of that, electrons will contribute to the current more compared to the holes. Even though the number is same, but the electrons will contribute more to the current compared to the holes, because electrons move in the conduction band where there is no bound electron, they are more free, there are empty space in the conduction band, therefore conductivity of electrons is more compared to the holes. But as I told you before, the conductivity of the intrinsic semiconductor, just now I explained, that is pure semiconductor, is very low. Okay, it is only because out of 10 to the power 9 atoms, only one electron hole pair is generated, only one bond is broken. This is called covalent bond broken. Covalent bond. If this covalent bond is broken, then only electron and holes will be generated like this. Okay, so out of 10 to the power 9 atoms, only one of the electron and hole pairs are generated, and only they will contribute for the current. Because of that, this intrinsic semiconductor has no practical utility because the current which we are getting is very, very less. Therefore, we have to have another kind of semiconductor that we call it extrinsic semiconductor. So in case of intrinsic semiconductor, these are the things that you have to remember. Number of electrons is same as the number of holes. Okay. Let's talk about extrinsic semiconductor. Extrinsic semiconductor is that semiconductor where we can get the good amount of current. Therefore, it has some practical use, but it is not a pure semiconductor. Okay, we have to add some impurity to the semiconductor. If you add some impurity to the semiconductor, then we will see that conductivity increases hugely. Okay, so therefore it's very important for extrinsic semiconductor to make. To understand that, we have to understand doping. What is doping? Doping is a process of adding impurity to intrinsic semiconductor in a controlled manner. Okay, so if you have a pure semiconductor, if we add some impurity to the pure semiconductor, it is seen that the conductivity increases very much, significantly. So that process of adding that impurity in a controlled manner, we call it doping. Doping can be achieved in many ways. One way is to add impurity to molten semiconductor. If you have a pure silicon in the molten state, okay, and if you add some impurity to that way also you can do the doping. Another way is to heat the semiconductor in the atmosphere of the dopant atoms. So what we do, there is a atoms which has to be added. Okay, so heat the semiconductor, germanium or silicon, in that atmosphere of the atoms, then also the doping can be done. Let's try to understand extrinsic semiconductor. So there are two types of extrinsic semiconductor, N-type and P-type. Okay, let's understand N-type semiconductor. In case of N-type semiconductor, what we have a let's take an example of silicon or germanium. They have 4 valence electrons. Okay, these are pure semiconductor. So in case of N-type semiconductor, we add arsenic or phosphorus as a impurity atom. Okay, so arsenic or phosphorus, both of them are pentavalent impurity. Pentavalent means the outermost shell has 5 valence electrons. So you have to add that atom which has 5 valence electrons, pentavalent atoms. So we can use any one of them, phosphorus or arsenic. So this is, you can see there should be 4 valence electron for the germanium, 4 valence electron for germanium, 4 valence electron for germanium, 4 valence electron for germanium. But if you add pentavalent atom, which you call donor atom also, so it has 5 electrons on the outermost shell. Out of the 5 electrons, 4 electrons will form the covalent bond with the other 4 germanium atom, but 1 electron will be free because there are 5 electrons in the pentavalent atom. And these 5 electrons, okay, if they get only at room temperature sufficient amount of energy to go to the conduction band, okay, if they go to the conduction band, then they will contribute for the current. So by adding impurity, what we are doing, we are increasing the number of free electrons. Okay, therefore here number of free electrons is more, therefore it is called N-type semiconductor. Okay, let me show it by picture this way. So this usually what happens, there is a valence band and there is a conduction band, and there should be energy gap. And energy gap for the silicon should be 1 electron volt, and for germanium should be 0.7 electron volt. Usually that is there. Okay, but if you add some impurity, some donor atom, pentavalent atom, then we saw that there is 1 free electron there, and this free electron has energy level close to the conduction band. Okay, it will have the energy level close to the conduction band, and this energy level we call it donor levels. Okay, that donor levels is the energy of this free electron. Okay, now you can see the energy gap is very less for this donor. The electron which is there on the donor levels, the energy gap is very less. It is just 0.01 electron volt. So only at room temperature, this electron which is there in the donor level can go to the conduction band. Let's now show it to you. This electron which is free can go to the conduction band. If they go to the conduction band, and if you apply the electric field, then they can move in the conduction band and they can contribute for the current. So at room temperature, all the electrons from the donor level will go to the conduction band. But there will be some electrons from the valence band also, they will go to the conduction band, and they will also contribute for current if the electric field is applied. Okay, but it is less. And once the valence electron will go from here to the conduction band, they leave behind holes. Okay, and this hole will also move in the valence band. Okay,
but most of the electrons will go from donor level and some of the few electrons will go from the valence band. So the number of electrons is more in the conduction band compared to the holes in the valence band. Okay, because holes will be only created if the electron from the valence band will go to the conduction band. But here, less electrons are going from the valence band to the conduction band. More of the electrons are going from the donor energy levels to the conduction band. So electrons in the conduction band is more compared to the holes. Therefore, this kind of semiconductors are also called n-type semiconductor. N-type means N for the negative charge, which is electrons. So majority charge carriers are here, electrons, and the minority charge carriers are here, holes. Okay, so in case of n-type semiconductor, these are the properties that you have to understand. Let's try to understand the concept of p-type semiconductor. In case of p-type semiconductor, what we do, we have again semiconductors, germanium, so silicon, which has outermost shell, 4 electrons on the outermost shell. We use trivalent impurity atom. Trivalent, that means which has 3 electrons on the outermost shell. You can use trivalent impurity as boron, aluminum, gallium, because they have 3 electrons in the outermost shell. So what happens here? 2 electrons, these 2 electrons are forming bond, these 2 electrons are forming bond, these 2 electrons are forming bond. So there are 3 electrons in case of trivalent atom. These 3 electrons are forming bond. But one of the electron of the germanium atom has no other electron to form the bond. So there is a hole over here because impurity, the trivalent impurity has only 3 electrons. So there is one hole, there is one space over here. So electrons from this germanium atom can easily go to this hole. Okay, and there will be hole created over here. Again, this electron again will move to this hole. Okay, so what is actually happening here is this. In the picture you can see there is a conduction band and there is a valence band. Okay, and this hole which you can see over here, for this hole the energy level is shown over here, acceptor levels for the holes. Okay, acceptor levels. So the electron which is over here, bound electron, these are valence electrons. Okay, electrons which is there in the valence band. Now this valence band electron can easily go to the hole because in the energy level you can see this acceptor level is very close to the valence band. So at room temperature only, these valence electrons from the valence band, instead of going to the conduction band, they can easily go to the acceptable levels over here. Okay, because energy required is very less. So more number of electrons will go to the acceptor levels. Okay, therefore more holes will be generated over here. So if the electric field is applied over here, then holes will move in this valence band, and because of this movement of this valence band, there will be current in the due to holes. But there will be some electrons still that will go to the conduction band, and some of this conduction band electron, if the electric field is applied, they can also contribute for current. But here the majority charge carriers are holes. Okay, because more of the holes will be generated compared to the more number of electrons going on the conduction band. So this kind of semiconductor, we call it p-type semiconductor. So here the holes are the majority charge carriers and the electrons are the minority charge carriers.